Greetings once again from the 5th annual John Chappell Natural Philosophy Society Conference.
A little louder, please.
Here in Seattle. Mercifully, this will be the last time you have to hear from me at this conference with my last talk. I'm Gallucci, and this talk will be on the plausibility of the Earth once having a thick atmosphere. And I'm going to look at an independent way to examine this by looking at the rate of impact cratering. Theories abound to how dinosaurs and other prehistoric creatures could have grown to such immense sizes. Some of these theories focus directly on changes in the governing physics of the universe, different gravitational constants. Some postulate that rather than this difference, the earlier Earth experienced lower gravity due to differences in size and mass. Most of the theories focus on biological and aerodynamical anomalies that may have prevailed to explain these gargantuan sizes. My paper tests the hypothesis that a much thicker atmosphere provided the buoyancy needed by these creatures to exist on land. I'm going to do an astronomical examination of possible differences in the rate of impact cratering on Earth due to atmospheric differences. My assumption is that a thicker atmosphere would burn up more meteors, reducing the cratering rate when compared to that during thinner atmosphere eras. This is the work of Levenspiel, Fitzgerald, and Pettit, their theories on how there were larger dinosaurs and flying dinosaurs. And to quote them, the giant flying creatures of the dinosaur age could only fly if the atmospheric pressure was much higher than it is now, at least on the order of 3.7 to 5 bar. Earth's current atmosphere is 1 bar. They postulate 3 possible histories for this atmospheric development. The lowest curve here, A, that is the pressure could have been 1 bar throughout Earth's earlier life, risen to 4 to 5 bars about 100 million years ago, and it's dropped back to what it is today. So kind of a geologically brief interlude of a much higher atmospheric pressure. The second one, the pressure was 4 to 5 bars from the Earth's beginning, 4.6 billion years ago. And around 65 million years, it could have begun to come down to today's 1 bar. That's the straight line B, again, dropping down. The third one is that the atmosphere could have started at a higher pressure, this is C, then decreased continuously through Earth's life to 4 to 5 bars, about 100 million. From them some more. Most of the carbon more than 4 billion years ago was in the form of gaseous carbon dioxide, monoxide, and methane. These carbon monoxide and methane gradually reacted with oxide minerals and were transformed into carbon dioxide. These reactions did not change the total amount of carbon in the atmosphere. Then they go on to do some comparisons with Venus. Venus currently has an atmosphere of 90 bars. Consisting of 96% carbon dioxide. Earth having a thinner crust, it was fragile and broke up. Venus's thicker crust remained rigid and did not permit removal of carbon dioxide from its bound state. In addition, because Venus is closer to the sun and hotter than Earth, free liquid water cannot exist on it, whereas Earth has giant oceans that remove carbon dioxide from the atmosphere. So if both Earth and Venus started out similarly with high atmospheric pressures, nothing's really changed to allow Venus to decrease its carbon content in the air. But for Earth, with the breaking up of the crust and then interaction with volcanic gases, etc., or other types of reactions, plus the presence of the oceans, a lot of this carbon was scrubbed out, and so we weren't at 90 bars like Venus is, and now we're down to 1 bar today. They observe on Earth that vast deposits of sedimentary carbonate rocks are found on land and on ocean bottoms, greater than 1 million cubic kilometers throughout the Earth's crust. Above the continents, the carbon dioxide-rich water reacted with rocks to form bicarbonates, followed by transport to the ocean and precipitation as calcium and magnesium carbonates. This forms deposits of chalk, or it was taken up by other living creatures to form giant reefs. How CO2 was scrubbed out of the atmosphere on Earth, unlike on Venus. Continuing with their theory, the concentration of carbon dioxide steadily decreased.
Closer, please.
The concentration steadily decreased primarily because of the formation and deposition of limestone and other carbonaceous materials. The concentration of oxygen slowly rose. These two changes thinned the forest and the dead material began to oxidize more rapidly. And this is evident because we can't find any massive coal deposits younger than 65 million years. Animal life flourished, first as very small creatures, then increasing in size, gradually leading to giant flying creatures that died out as the total pressure of the atmosphere dropped below their sustainable level. Assuming that the Earth's atmosphere was very different, that would answer some puzzling questions, at least according to Levenspiel, Fitzgerald, and Pettit. Flying creatures from the age of dinosaurs, why there were such things, when physiology, biology, and aeronautics say that this was impossible, at least given today's conditions. Astronomy says that the Earth was too cold to sustain life. And a lot of theories are that the Earth was much warmer at that time. If Earth's atmosphere had stayed at about 1 bar, why then did we have the equivalent of 50 to 70 bars of carbon dioxide and limestone and other carbonates? Where did that all come from? When taken together, the evidence leads to the same conclusion. Atmospheric pressure was higher in the past than it is today and consisted primarily of carbon dioxide. So that was the theory of Levenspiel, Fitzgerald, and Pettit. Now, David Esker, in his work, he believes that the large dinosaurs and pterosaurs of the Mesozoic era present a scientific paradox as well. They would have had insufficient muscle strength, insufficient bone strength, unacceptably high blood pressure within the tallest dinosaurs, and the paradox of pterosaurs having grossly insufficient powers to fly in atmospheric conditions similar to the present. The dinosaurs' relative strength would be substantially less than that of large animals of today. Archimedes' principle states that when an object is partially or fully submerged in a fluid, buoyancy lifts up the submerged object that exactly equals the weight of the fluid displaced. The main difference provided by the fluids, air versus water, is the amount that needs to be displaced to achieve flotation. For terrestrial vertebrates, it is the net force produced by their weight that often limits their size. But this is true for species that exist in the water. In fact, the blue whale is considered larger than any dinosaur that ever existed. To produce an effective buoyancy force on dinosaurs, the Earth's atmosphere would have to be comparable to the density of water. If you sum the forces acting on a typical dinosaur, the density of the necessary atmosphere would have been 670 kilometers per cubic meter, which is 2/3 the density of water. Continuing with Esker's theory, 150 million years ago, the Earth's atmospheric pressure near the surface was about 370 atmospheres. That's 370 times thicker than what it is today, and it just happens that at the average ocean depth of about 3,800 meters, the pressure is about the same as it would have had to be at 380 atmospheres. So for all practical purposes, the present-day pressure at the average depth of the ocean is the same as the pressure at the bottom of the Mesozoic atmosphere. Yet there are numerous species that live at this depth and many more that live much deeper. Therefore, the extremely high pressure of the Mesozoic era had no ill effect on the terrestrial species of that era. Within the Phanerozoic era, which is the current geologic eon, during which abundant animal and plant life has existed, and that goes back to 541 million years ago, when you had the, I guess it's called the Cambrian or Precambrian explosion. We can identify 2 thick atmosphere eras and 2 thin atmosphere eras. Twice during the Carboniferous and the Cretaceous-Paleogene periods, the atmosphere transitioned from being extremely thick to relatively thin. With a massive amount of carbon dioxide being removed from the atmosphere, we would expect to see large carbon dioxide deposits during these times, and that happens to be the case. This is taken from Esker's chart showing the variation in the atmosphere. This is going back, this is 400 million years ago, and we're getting closer to today. It's not a strictly piecewise linear curve. I linearized it just to make it easier to draw, but it follows this general shape. I tried to assign, he says there's 2 thin and 2 thick eras, so I arbitrarily made the transition point at 200 atmospheres, and that gave me two thin eras, when it was below 200 atmospheres, and two thick eras, when it was above 200 atmospheres. And the transition points are at 340 million years ago, 230 million years ago, and 53 million years ago. And this thick one era I didn't show, this would run all the way out to the formation of the Earth 4.6 billion years ago. Now let's look at the lunar cratering rate. Ascertain the time history of what the cratering rate would have been for the Earth in the absence of an atmosphere, its geologic activity, etc. And this is the assumption is that the time history of the moon's cratering rate, based on what is called the constant production rate curve, which is this dotted line here, would be closely representative on a per unit area, given its proximity to the Earth. So I'm saying essentially the moon is just like the Earth would be without an atmosphere, so its cratering rate is more representative of the amount of asteroids and meteors in the vicinity of the Earth throughout history, and it's not unlike the That was my hypothesis going into this. In the Earth, the cratering rate, a thicker atmosphere should burn up more incoming meteors than a thinner one. I found the Earth Impact Database, which lists all the Earth craters that are greater than 4 kilometers. And the reason I use the ones greater than 4 kilometers is because that's consistent with what the moon works with. The moon curve here is also for greater than 4 kilometers. So I limited my database to those for comparison. 163 craters were identified, and that reduces to 111 if I truncate from at the last 10,000 years at the last ice age, roughly up to the end of ice age, affecting only the last Esker era. And so that just means that I can look at for the Earth, I can look at two time intervals. I can look down to time 0, which is present, or down to time 10,000 years ago, which is almost 0, but as you can see, it has a significant effect on the number of craters. It knocks off 52 craters. This arbitrary truncation is to compensate for the preponderance of North American craters of most recent age relative to similar craters worldwide. And that's intended to remove a possible bias from more extensive crater identification having been formed on our continent in recent times. But I will look at the results for both, down to the 10,000 years ago and down to the present. Cratering rate comparison. This is the atmospheric eras for Esker. I started at, the thick one started at 2.4 billion years ago, finished 340 million years ago, then thin one. These were those transition points that I showed earlier on the curve. The lunar cratering rate from the previous graph for lunar shows what the cratering rate was per square kilometer at the start and the finish. So given that these are order of magnitude type analysis of ranges, I used the geometric mean to characterize each one of the eras. And then doing a weighted average of time over time. This was the average cratering rate for the two thick eras. This is the average cratering rate for the two thin eras. And so if I look at the cratering rate during the thin and thick era, I see that it's 0.245. Now, obviously the moon doesn't have an is that during these 4 eras, the cratering rate in the vicinity of the Earth, the influx of meteors, was different. And it was, during the thin era, it was lower than it was during the thick era. So that's the base I need in order to do my Earth analysis, which gets compounded by an atmosphere, geology, etc. So for each Esker era, I estimated the cratering rate on the moon and Earth. For the latter, based on 29% of the Earth's surface area that is land. So again, the moon, I have to work only with the part of the Earth that's land. These are again, the same atmospheric eras for Earth. These are the cratering rates Now the way I determined that is there's a number of craters were listed for the different eras, and then this is the area of the Earth weighted by the time, and then I weight over the two thick and thin eras by doing a weighted average looking at the two time intervals here by this calculation. So what I got here is for the two thick eras, this was my average cratering rate for Earth. The two thin eras per kilometer squared. So I find that for the Earth, the ratio of thick to thin cratering rates is 0.542, which is about twice as high as that for the Moon. Now this was first analysis was from the Earth to the end of the Ice Age. Again, remember I truncated one analysis truncated the crater count 10,000 years ago. If I go to present, you can see this last group, thin 2, adds on the 52 craters that I would have discarded earlier. If I do the same analysis, I find that the ratio of the thin to the thick era is actually higher, 1.26. The key thing here is not what these values, the absolute value of these values, but their comparisons relative to the Moon. During the thick eras, the Earth cratering rate is 59 times lower than the corresponding lunar cratering rate. And that's to be expected given Earth's active climate and geology. The thin eras, Earth's cratering rates vary by a factor of about 2.5. It's lower when it's truncated at the end of the Ice Age, higher when I go down to present because they've counted a lot of craters in North America. They're easier to find, and there's probably been a lot more geology work, etc., done here, so it's kind of a bias for the last 10,000 years. However, the important thing is that both are lower than the lunar cratering rate for the corresponding thin eras, as would be expected, but notably not lower by as high a factor when compared to the thick eras. So for the thick eras, the ratio was about 59, but for the thin eras, it's only 26 and 11, and this does take into account that there were different cratering rates, absolute cratering rates during those eras on the Moon, which would have also impacted, those same meteors would have impacted the Earth. And so you would have expected to see the same type of ratio for the Earth and the Moon if the Earth didn't have an atmosphere, didn't have geology. So assuming the geological effect of erasing craters isn't that great, then it seems like this difference can be attributed to atmospheric differences for the Earth. Consider the ratio of the weighted cratering rates. When truncated at the end of the Ice Age, Earth's thin era cratering rate is reduced by a factor of about 2 relative to that for the thick era. Somewhat to be expected given the lunar result, which showed a reduction factor of about 4. The Earth cratering rate during the thin eras being reduced by less compared to the Moon rate may indicate the effect of atmospheric thickness. So again, it's the difference in the ratios that is key here. That is, the thinner Earth atmosphere allowed more cratering during the thin eras than would be expected relative to the cratering rate during the thick eras when compared to what it would have been for the Moon, which is climatologically and geologically dead. Again, comparing the ratios of 0.54 Earth to 0.245 Moon. Here's a graphical representation considering the ratio of the weighted cratering rates. Without truncation, that is to present time, difference is much more pronounced. Earth's cratering rate during the thin eras now is slightly higher than during the thick eras by about 1/4, ratio of 1.6. Here's the different trend lines. Here's the Moon cratering rates for the combined thick and the combined thin eras, shown as the red line. The dashed green is the same for the Earth when I truncate at the Ice Age. That's also a decrease, but it's not as sharp a decrease for the Moon. And if I look at the Earth to present time, is actually a slight increase from thick to thin. Probably that one I don't consider as representative because I think there's the bias in the recent North American craters. So the key ones are comparing the red to the green line and the fact that the green line is not as steep as the red line. The Earth to present trend is completely different from the lunar, which saw a reduction by a factor of about 4 rather than increase by 1/4. This may indicate even more so the atmospheric thickness effect, although the caveat previously mentioned about the preponderance of the more recent craters having been identified in North America somewhat tempers this. Nevertheless, if I look at the Ice Age truncation comparison, there's a noticeable difference relative to what would be expected for a body without an atmosphere subjected to the same meteor influx represented by the moon. Again, this trend here is more gradual than the one for the moon. This is the Earth. Likely less dominant could be decreasing geologic activity with time, since the thick eras each preceded the thin eras, though likely not decreased as much over the past 2 billion years. I don't think Earth's geological history has changed that much in the last 2 billion years. Clearly, in the previous 2 billion years when it was forming, a lot of volcanoes erupting, may have been molten, etc., but it's probably a lot quieter, has been quieter recently. In summary, given all the assumptions and approximations and the fidelity of cratering data for both Earth and Moon, no definitive conclusion can be drawn. However, this cratering rate analysis, which is independent from the aerodynamic analysis that Esker and Levenspiel et al. Looked at, this does not contradict that Earth's atmosphere has varied substantially in thickness and offers an independent test of the hypothesis to supplement the more biological and aerodynamic ones that those analysts provided. Due to the thick atmosphere era, meteor impact on the Earth would be decreased by a relatively greater degree versus the thin atmosphere era when compared to the expectation for the geologically and climatologically dead moon. That concludes this talk, and this is for Dave. You want to take a picture of the poem I wrote yesterday?
I'll get a copy of it. Maybe you want to read it for us?
Okay. Chappell after 5. We've been alive for 5, society's Chappell, continuing to thrive while physics false dispel. We question everything, especially tenets of what mainstream physics flings as lightning from above. Did early Earth expand? Does ether still exist? Rejected out of hand by mainstream physicists. But still we persevere, for know the book's unclosed, despite 100 years since Church of Einstein rose. Surprise. And I was kidding with Duncan earlier that we've now had and the only one where there was the least bit of disorder happened to be the one in Vancouver. And we all know that Canadians are much better behaved than Americans, so I'm not sure. I think we may need more judges if we have any more in Canada to keep the order. So this one, again, I slapped this together this morning when I was walking. Duncan has a theory. Ether's everywhere. Dad sees G1s clearly, bouncing through the air. Musa says electric, fields explain it all. Cameron's rejected, universal law. Dave believes in crisis, since Sir Isaac penned, treatise of the highest science he could then. Gerald shows that water's not a simple thing. We again disorder to what's mainstream bring. And from now on, Bob the Hilster will be known as Dad. He has been adopted as the official dad of the group.
And it's not right to abuse your elders either.
That's right. That's right. Especially those that are directly related to you should never abuse you.
Okay, do we have some questions? I do have a question. When you were calculating the craters, were you, let me change the slides here, but were you also taking into account that, what, 3/4 of the surface of the Earth don't have cratering because we don't know what's going on?
Yeah, that was, as I showed here, based on 29% of the Earth's surface area that is land. I had to do the reduction, the cratering rate only over the land surface.
And also, I'd be curious to, I sort of get the idea of what you're trying, this is sort of related to the Earth expansion, is that right? Or is this...
This would be independent of whether or not the Earth expanded, because in the dinosaur era, the Earth was super tiny in the beginning, and then after a couple billion years, it started to obtain oceans. Now I forget just how much around, see, dinosaur era, about 100 million years ago, how much of the Earth had some oceans by then. But I think the continents basically haven't changed in shape. And I think I don't know how much more land there would be now, because I guess the continents do get wider. They do get more surface area, but if anything, that would mean that the cratering rate in the earlier mark, and then instead of dividing by 29% of the current Earth's surface area, you would be dividing by whatever fraction of the Earth's surface area was land back then. And I suspect that, depending, I don't know, there may have been more land, there may have been less land, it depends because how much ocean there was back then. And again, you'd have to look at the different Earth projections by the different expansionists in order to know which one you'd want to use. But you could do that. I mean, around 100 million years ago.
Also, with the obviously there's the argument that about the atmosphere. What did you find in this research for the argument for those people? Obviously, mainstream is not following expansion tectonics, but what did you find in this research and exercise with the atmosphere as an argument for? It sounds like you're sort of, maybe I'm just totally off, but it sounds like it's somewhat of a reinforcement of the possibility of the idea that the Earth didn't expand and that a lot of this what we're seeing is really an atmospheric thing, or did you find contrary to that?
Well, this analysis, none of the analyses I found addressed an expanding Earth. They all assume that the Earth was a constant size.
Sure.
So they don't use that as a possible explanation. So if you assume the Earth and the Moon too have remained at the same size, then this lends plausibility to the thicker atmosphere argument. Now, if you think the Earth has varied in size, James I think then you get into some of the governing physics of the universe, and there are some postulates that earlier Earth experienced lower gravity due to differences in size and mass. So I guess if you're Earth expansionist, you would argue that maybe gravity was lower, because obviously if the Earth was smaller, 1 over r squared, if the Earth had the same mass as it has today but was smaller, it would be denser and would have had a much higher gravity. So in order for the gravity to be lower, the probably exponentially exponential dependence of mass with time.
It's more on topic of what David has just been raising. How can there not be expansion if one starts with the concept that a cosmic body is a collection of stuff that is floating through the universe, and it starts to grow, starts to rotate, starts to have eddies around it, and bit by bit, a star is born. A star, it's not a star at the beginning, it's just a collection of stuff, but then grows and grows and grows. It seems to me it has to be that way, because you can't just snap your fingers and you got a star. To me, that doesn't make sense. And if that's the case, if what we see out there is the product of a slow collection or a collection of stuff growing, how can there not be an expanding Earth? It seems to me that the common sense is inevitable. Do you have any comment on that?
Yeah, the problem that if it's a steady accumulation of the same material, then the density of the Earth will stay the same. And while the mass will grow, the not the clearly the Earth. I mean, if you just keep adding stuff, the Earth's going to get bigger and bigger. So that could argue for dinosaurs being bigger. That's one.
Okay, thank you.
Yes.
He needs the mic.
Yes. Let me say that Dr. Raymond Gallucci is so rich in his presentation.
Oh, thanks.
I think our atmosphere, will that amount to more oxygen, more carbon dioxide?
Their theory is more, the theories I came across were more carbon dioxide.
Okay. It seemed to me that gravitation should be a bigger factor in determining the size of creatures than the thickness of the atmosphere.
Yeah, well, like I said, there's different sets of theories. There's theories on that some think the gravitational constant changes. I think, isn't Bill Lucas one who's advocated a change in gravitational constant with time? He's not the only one. I've seen a lot of people there's people who think the speed of light has changed with time. There's people who think the gravitational constant has changed with time. So there's a set, again, I didn't look at all the explanations for big dinosaurs. There were three groups of explanations fall into three categories. There's the changes in physics. There's the third one. So for the third one, constant size Earth, no change in the physics or gravity, then an independent nations are trying to choose one over the other. I just looked at one family of explanations and tried to find whether or not it was plausible. So I found that it's plausible that if you assume the Earth has not changed its size, gravitational constant hasn't changed, it's plausible that variations in atmospheric thickness and pressure could explain
Earth, where we can send geologists to make guesses as to how old these things happen. But on the moon, I think we only got pictures, right? So how do we determine that?
I don't know how they determined. I found that this is, I mean, here's the reference. And lunar production rates from the measurement of crater densities on the lunar surface and from absolute age dating of returned lunar rocks. Firm correlations can be constructed for the well-characterized basalt surfaces, 3.8 to 3.2 billion years, and the contemporary meteorite flux based on current astronomical observations, t equals 0. So it looks like they've got a bunch of data here. They have data around here. The ages of Tycho and Copernicus are inferred from indirect evidence. So here's their data points. They've got Earth craters, they've got Tycho and Copernicus, they've got basalt surfaces here. So I think that's why they have this range, this uncertainty range in the lunar cratering rate. And then I guess this is their best fit here. So again, I didn't really look into how they determined it. I looked for, somehow I was looking for, is there any data on the lunar cratering rate, and I found this.
I think part of it, I would imagine, Franklin, is that they also know by just literally erosion and wear and tear. I'm sure there's visual cues as to how old things are as well. I think that's, cosmology abuses that to heck, but I think imagine. Okay, any more questions?
One point is, unfortunately, a lot of these analyses here, we're forced to use data that is compounded by mainstream, and so there's no way to throw, to completely whitewash any of these analyses. If you're going to do a quantitative type thing, you're kind of stuck using some of the mainstream material. You try to minimize, you try to use the stuff that isn't too controversial, but it's unavoidable that some of it comes into play. Like, there's probably people who will argue that the size of a proton could be many orders of magnitude different, sizes of electrons. When I do an analysis, I take the traditional size of an electron, size of a proton, mass of an electron, mass of a proton, which of course